Welcome, students. We are going to discuss RSA crypto system. Um, the way it is discussed here is not in the implementable form. There are a lot of security parameters you have to look at before you implement it. But nevertheless, let's discuss the algorithm behind it. So the idea is, again, Alice wants to send a message to Bob securely. So she uses Bob's public key. So let's see how it works. So Bob starts with basically Bob chooses two primes, P and Q, uh, and let N be P and Q, P times Q. So note that again, there are ways to choose these primes. These primes have to be big. They have to be 124 bits, and they should not be close to each other. So there are many security concerns about P and Q as well. Okay. Then he chooses E, a positive integer, such that GCD of E and phi of n is 1, where phi of n is the Euler phi function. Or Euler-Taussian function. Then he computes a value D such that D is the inverse of E modulo phi of n. Then the public key, Bob's public key, is pair NE. So he makes this public. And the private key is P, Q, and D. Then suppose Alice wants to send a message. So Alice basically, for any message m less than n, encrypts m using c equals to m to the power e. So m is the message. We are thinking about m as a number less than n, and the encryption goes m to the power e as c. And then when Bob receives this message, so Alice say computes the ciphertext c equals to m to the power e mod n and sends to what? Sends to Bob. And then Bob decrypts c using m equals to c to the power d mod n. Okay, so let's work out the example. Again, to emphasize that NE is the public key and PDE is a private key. All right, so let's look at an example. So Bob chooses P to be 101 and Q to be 113. Yeah, where of course P and Q are primes. Right? So this is of course an insecure example, right? I mean, like this is not secure, right? I mean, if you work with these, they can be quickly broken. So you need really large primes, like, okay. So however, then compute. So Bob chooses, so this is what Bob does. First chooses P and Q, computes. So he needs to find E such that phi of n is 1. Now note that once you know P and Q, P of n is simply P of P times phi of n. So that becomes 101 minus 1, 113 minus 1, which is 100 times 112, so 112 times 0, 0. Yeah, so this is easy to compute, right? Easy to compute, right? Because after all, the encryption and decryption should be done easily if they are done logically, right? So then he computes this, and then he chooses. So then step 2, chooses E such that E comma phi of n is 1. So I will make that choice already. So let E be 3533. Okay. So he randomly chooses E such that E and phi of n are co-prime. All right. So checking that also is not hard. All right. You can run the extended Euclidean algorithm to check whether they are co-prime or not. Third, then basically Bob also computes, Bob calculates D such that DE is congruent to 1 mod phi of n. Again, what is the Euclidean algorithm? Extended Euclidean algorithm. So all these computations are quick, right? They're not expensive at all. Then Bob publishes, so for Bob publishes n as 1, 1. So what is n here? N was multiple of PQ. So n is PQ, which is 1, 1, 4, 1, 3. Then Bob publishes n, which is 1, 1, 4, 1, 3, and the public key, which is 3, 5, 3, 3. Okay. Now here, when Bob computes D, he gets D equals to 6, 5, 9, 7. Okay. So now this is public, all right? So this is public. Now suppose Alice wants to encrypt a message. Encrypt, say 9726. Yeah, while choosing the the message, all I want is this message has to be less than n. So Alice chooses Bob's public key. So chooses Bob's public key, and computes 9726 to the power 3533 mod n, which is mod 11413. It turns out that this is 5761. So this is your plain text. So plain text. This is the ciphertext, and then sends this to Bob. Okay, so and computes this and sends to Bob, and sends to Bob. 6, Bob decrypts by computing 5761 to the power 6597 mod 11413, which turns out to be 9726. This is the plain text, right? So plain text. this is how the algorithm works. Okay, so let's work on another example. So suppose you have two primes, P is 43 and Q is 59. So you compute N equals to 43 times 53, which is 2537. You take N equals to 13, you can see that N is, so phi of N is 42 times 58. So 13 is already coprime. Then he encrypts the message. One way of encrypting the message, say message is public key cryptography. So let's forget about the space. So P basically is 15. Then you have U is 20. So you see the first one is 15 and 20. Then basically he chooses next one. So L, so B is 0, 1, so 0, 1. L is 11, so 11, and so on and so forth. And the last one is Y, which is 24, and you just keep it in pairs of, as a 4-digit, he basically uh, pads it by extra 23, which is a symbol for X. Okay. So again, this is not necessarily the way you should do it. This is one of the suggested way you can convert the 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 message into a plain text. After all, a plain text has to be a number, right? Then the encryption is as follows. So Bob's public key now is E, which is 13, and public key is 13, and N, which is 2537. Now the private key should be, so Bob's private key is going to be 937, right? So we'll come to that in a minute. So how is the encryption done? So for each block, you raise it to power, block to the power 13 mod n, which is mod 2537. For example, 5120, the first block to the power 13 mod 2537 is 0095. So this is the ciphertext coming out of the plain text. Okay. Now, how does the decryption works? So Bob sets out private key is D, P, and Q. So he uses D in the following way. So his D is calculated as D is E inverse modulo P of N. And that can be seen as basically, so 937 is mod inverse of 13 mod 243. So then he computes P, which is, so P is C to the power, the ciphertext to the power 397, which is same as P to the power 13 times 937, which is same as P to the power 2436 times 5 times P. But we already know that P to the power P of N is congruent to 1 mod N, right? So you get this is 1 mod N, so this will become P times 2537. So this is how the decryption is done. Now, why is RSA secured, or was secured at least now? So note that when you take a plain text P and you raise it to the power, say P to the power E mod N, this is, the belief is that this is a one-way function. That means it's easy to compute. As you can see, you can do fast modular exponentiation, but it's hard to invert. And the security lies on this to, to compute P from P to the E, we need inverse of E mod phi of N. We need to compute So we need to compute phi of n, for which we need to factorize n. Yeah, and the factorization is a hard problem, as we'll see, as we have seen already with the primitive factorization method, that it doesn't seems that straightforward. So now let me verify. So let's quickly verify the following, that encryption and decryption are inverses of each other. So verify that encryption so we just want to verify that encryption and decryption process are inverses of each other. What do I mean by that? So the idea is, so you have this, suppose you have P, which is the plain text, and that goes to P to the power E mod n. And let's call this step as encryption step. So this is a function, it's said to be a one-way function. So P to the power E, and then we have encryption, where you have chosen E in a way that E and phi of n are relatively prime, right? So similarly, we have D, just choosing to call it dk, where the function is basically you send anything, say x to x to the power d mod n. So now we know that ed is congruent to 1 mod phi n. This implies there exists k belonging to z such that ed equals to phi n times some other number, say t plus 1. So now suppose you have a message p, which was then sent to compute p to the power e. So this is plain text. This becomes ciphertext. And then when you apply, so you are applying exponentiation by e, and then you raise it to power, raise to power d. So you get p e to the power d, and then we have p e to the power d, which is equal to p to the power phi of n times p mod n. Now p to the power phi n is congruent to 1 mod n, so this is going to be p mod n. So you see, so we have shown that this encryption, basically here ek, and then after that you apply dk, they basically leave to the, so ek and then applying dk on your plain text brings you back the plain text. Okay. So again, there are a lot of issues to discuss here, namely the following. Here we are using Euler's theorem when p and n are co-prime. Now what happens when p and n are not co-prime? So in that case also it works. So there are a lot of issues to discuss here, but I think this is a cool application of your factorization problem, right? So this is called RSA, and named after their founders, Ron Rivest, Adi Shamir, and Leonardo Edelman. Thank you for your attention. Bye.